In previous chapter, we learned about the multi-head attention mechanism, one of the core components of LLMs. In this chapter, we will talk about the other building blocks of an LLM and how assemble them into a GPT-like model that we will train it in the next chapter to generate human-like text. The LLM architecture referenced in this figure consists of several building blocks. We will begin with a top-down view of the model architecture before covering the individual components in more detail. The GPT model shown here, in addition to the embedding layers, consists of one or more transformer blocks containing the masked multi-head attention module we previously discussed about. In the rest of this chapter, we are focusing on GPT-2 because, first, OpenAI has made the weights of the pre-trained GPT-2 model publicly available. And second, GPT-2 can be run on a single laptop computer. GPT-3 is fundamentally the same in terms of model architecture, except it's scaled up from 1.5 billion parameters in GPT-2 to 175 billion parameters in GPT-3. And also it's trained on more data. GPT-2 can be implemented in 4 different sizes depending on our needs. The system parameters according to these model types are shown here in this table. Number of attention heads, number of stacked units, embedding size, number of parameters, and vocabulary size. As mentioned before, GPT-2 LLMs come in several different model sizes, ranging from 124 million to about 1.5 billion parameters. The core architecture is the same, with the only difference being the embedding size, the number of times individual components like the attention heads and transformer blocks are repeated. As the start point in this slide, you can see an illustration of a typical transformer block where the input tokens have been embedded into 768 dimensional vectors. Here, each row corresponds to one token's vector representation. The outputs of the transformer block are vectors of the same dimension as the input, which can then be fed into subsequent layers in an LLM. As shown here, each transformer block contains the masked multi-head attention module, to layer norm module, to drop out backs, the feed-forward neural network with GLU activation function, and some linear layers. In previous chapter, we learned about the masked multi-head attention module in detail. In the rest of this chapter, we are going to discuss about other components respectively. An illustration of the layer normalization is shown in this figure. In this exemplary illustration, the 6 outputs of the linear layer, also called activations, are normalized such that they have a 0 mean and a unit variance after normalization. For normalization of the d-dimensional vector x, we use these mathematical formulations where mu is the mean and sigma is the variance of the vector x. And this is our mathematical formulation for normalization. Okay, now we discuss about the dropout mechanism that's used to prevent overfitting. Dropout works only during the training phase. In dropout mechanism, each neuron's output in the dropout layer is set to 0 with a fixed probability p. That's usually named the dropout rate. The active neurons then are scaled up by dividing their output by 1 minus p. This is because we want to ensure that the total output magnitude of the layer remains approximately the same during training as it will be during inference when all neurons are active. Note that the dropout mechanism is only active during the training phase. It's disabled during inference when the model is generating text. Now let's consider explaining about GLU activation function that's used in feed-forward neural network. As we can see here in these plots, GLU is very similar to ReLU. That's a famous activation function in neural networks. Actually, ReLU is a piecewise linear function that outputs the input directly if it's positive. Otherwise, it outputs 0. GLU is a smooth nonlinear function that approximates ReLU, but with a non-zero gradient for almost all negative values. Here is an overview of the connections between the layers of a typical feed-forward neural network as a main part of the transformer. It shows how the embedding size is manipulated inside this small feed-forward neural network when we pass it some inputs. This neural network can accommodate variable batch sizes and numbers of tokens in the input. However, the embedding size for each token is determined and fixed when initializing the weights. This is an illustration of the expansion and contraction of the input and output linear layers in the feed-forward neural network. In this example, first, the input is expanded by a factor of 4 from 768 to 3072 values. Then the second layer compresses the 3072 values back into a 768 dimensional representation, expanding and contraction. Now we are going to discuss about the necessity of shortcut connections. In this figure, the left one, a deep neural network consisting of 5 layers without short connections is shown. As you can see here in this structure, the gradient values in early layers become vanishingly small. Here the gradients denote the mean absolute gradient at each layer. To avoid this issue that's usually named gradient vanishing, in the right figure, the shortcut connections are added in each layer, as you can see here. Shortcut connections involve adding the inputs of a layer to its output, effectively creating an alternate path that bypass certain layers. Okay. The summary of what we have discussed so far about the components of a transformer is illustrated in this figure. In this typical illustration of a transformer block, the input tokens are embedded into 768 dimensional vectors, where each row corresponds to one token's vector representation, and the output of the transformer block is also vectors of 768 dimensional, the same as the input, which can be fed into subsequent layers in an LLM. This is an overview of the overview of the GPT-2 small model architecture, showing the flow of data through the model, starting from the bottom. Tokenized text is first converted into token embeddings, which are then augmented with positional embeddings. This combined information forms a tensor that's passed through a series of transformer blocks shown in the center, which are stacked on top of each other and repeated 12 times. The output of the stacked transformers is then passed through final layer norm and last linear layer that embeds each token vector into a 5,257 dimensional embedding, where this number 5,275 is the size of the vocabulary. As before, each transformer block contains multi-head attention and feed-forward neural network layers with dropout and layer normalization. This is the step-by-step process by which an LLM generates text, one token at a time. Starting with an initial input context, for example, hello, I am. The model predicts a subsequent token during each iteration and appending it to the input context for the next round of prediction. As shown, the first iteration adds 1, a. The second adds model, and the third adds ready, progressively building the sentence. As mentioned before, as a part of the input preprocessing pipeline, the input token is first broken up into individual tokens. These tokens are then converted into token IDs using a vocabulary. Then the token IDs are converted into embedding vectors to which positional embeddings of a similar size are added, resulting in input embeddings that are used as input for the main LLM layers. In the following slides, we are going to discuss about the post-processing pipeline. That's highlighted here in this figure by this circle and this arrow. To describe the whole process of text generation in a GPT model, consider this example in which the input context is "Hello, I am." The goal is predicting the next token. As before, the input text is first broken up into 4 individual tokens: hello, comma, I, and am, with these token IDs. These token IDs are then converted into 4 embedding vectors, and the resulting embedding vectors are fed to the GPT box. That's actually the stack of transformer blocks and the final layer norm and linear layer. The output of GPT box is a matrix consisting of 4 vectors, each with 5,257 dimensions. In step 3, as a part of post-processing, we should extract the last vector, which is supposed to be related to the generated text token. This one. Okay, these logits are then converted into probabilities using softmax function. See step 4 here. Now we consider the largest value of probabilities. The corresponding position in the vector represents the ID related to the generated token. In this example, the generated token ID is 257. That's related to the word A in the vocabulary. This illustration shows the 6 iterations of the token prediction cycle, where the model takes a sequence of initial token IDs as input, predicts the next token, and appends this token to the input sequence for the next iteration. Okay. In the next chapter, we will learn about training the LLM parameters. That chapter explains about implementing the training function and pre-training the LLM, about saving and loading model weights to continue training an LLM, and about loading pre-trained weights from OpenAI. If you have not done so yet, please join our community by hitting the subscribe and notification bell. Thank you.